Okay, we're going to do a very short lecture here on admittance parameters, which follows the pattern of the impedance parameters very closely, except we're dealing with admittance rather than impedance. So that's the inverse. Okay, so here we have the same network. Haven't changed the picture at all. I1, V1, I2, V2, and they're just the way they are. But now we're going to talk about admittance, the inverse of impedance, but how does this really show up in equations? Well, we just, instead of being open circuit, we short circuit the opposite port. So if we're finding the port parameters for the input port, such as indicated here, Y11 and Y21, this is the influence of a current on the output to the voltage on the input. All right, I just looking at a short circuit. I reverse the situation because I'm calling the ports input and output, but that isn't implicit in networking and in two-port network notations. These are in fact just called the short circuit admittances. Okay, you short the circuit instead of open circuit, and then you're looking for current over voltage instead of voltage over current. Okay, the equations are the same, and they fall into a matrix form like that, but you still have the two equations relating, right here relating. Here's the input on its own, and here's the relationship of I1 to the second terminal. Here's the relationship of I2 to the first terminal and I2 to itself. Okay, that terminal to itself. All right, so this is exactly like the impedance parameters, except we're inverting. We're making equations now for I as the dependent variable, and the independent variable is V. Okay, so here's that summarized. You have these pictures in your text, of course, but it's pictorially, there's the short circuit that we're dealing with. Here's still the equations, right? And I've copied these down here, just referenced them, which is really nothing but these equations right here, copied here, with the notation that when I solve it, I'm going to have a zero voltage on whatever terminal is indicated. If I'm finding a value versus V2, I want to find it when V1 is 0, so that means I'm going to short circuit it. So this is referring, of course, to this case right here. That one. All right. Now let's take a couple of special cases. Oh, well, one special case. Here's the reciprocal case, right? And reciprocal, so this is the reciprocal. Hope I spelled that right. The reciprocal case, and the reciprocal case is what? If I'm down here, the reciprocal case is where this term equals that term. When those are equal, I have reciprocity. Okay? And so, but now notice the shape here is what we call the pi equivalent circuit. There's the two types. For the z parameters, we went with the t equivalent. For the y parameters, we're going with what we call the pi equivalent because it looks like the character pi. Okay? Now, likewise to, or similar to the z parameters, we could do some quick calculations here. For instance, the current right here is going to be what? V1. Now the temptation is to divide by something because that's Ohm's law. But when we have admittances, we just multiply by them, right? Because they're I over V. So this would be y11 plus y12, right? And the current here, whoops, if I've short-circuited this, right? When I short-circuit that, this is a non-player, right? It's the same as putting the short right through here. So this current is what? Now it's V1 times minus Y12. So if I calculate for I1, I get I1 is equal to V1 times Y11 plus Y12 minus V1 times Y12. So this is V1 times Y11. Okay, same thing happened in the T equivalent circuit for impedances, right? What you can notice is in the pi equivalent, we're really chasing current, right? That's what the equations are about right here. They're about current. And so we need a circuit that the transmission element, the shared element right here, is current based, right? So it needs to know about current flowing through it. When we did the T equivalent, right, we had this, and this, because the shared element was voltage. We wanted voltage across something. Here we want current. Current is a flow through. It's shared. So a little bit of a picture as to why this is the chosen circuit, because it really represents reciprocity the best. The one element, if those two are equal, if y21 equals y12, then this best represents that case. Okay, here's the general case, just like before, right? So this represents this as the general case. All right, where you have current sources, y12. This is when y12 is not equal to y21. I mean, it can be equal to y21, but when it is, then these two current sources basically merge and they become summations, okay? So that's what's happening in these models, and these are just model representations. What you may have seen before, and you may remember, this begins to look a lot like the transistor output right here, right? And so this begins to look startlingly close to the transistor model that we like and use so frequently. So that's why the admittance parameters, you know, they have some weight, some strength. They're not to be lost easily. Let's take a quick look at one. I'll just keep these couple of pieces and look at a simple problem here. And I'll do the practice problem 19.3. You have some excellent worked out examples and so forth. So 19.3 has, you start with a T network, so this would be interesting. It's almost like a conversion problem, right? So there's our two ports, number 1 and port number 2. And this is real simply 1, 2, and 3 ohms. And these are ohms, not mhos, which would be admittances. Okay, and if we want to find one of the parameters, let's just say we want to find y11. Okay, so y11, we've got, oh, I should have brought those up, the equations, but we know what they are. They're right here for the case of V2 equals 0. I mean, they're implied here in all of this. So y11 is equal to I1 over V1 when V2 is 0. So let's find that. When V2 is 0, we'll just short this out. So I'll redraw the circuit here in case we want to use it again. So we've got this. When V2 is 0, we've shorted this out. So we've got 1 ohm. And now we've got these two in parallel. A 2 and a 3. Right? So that whole thing is equal to 2 times 3 over the sum 6/5 of an ohm. So the total here would be 11/5 ohm. Okay? So now there's my I1 and my V1. So Y11 in this case is going to be 11/5. Well, let's do the whole thing. I1 is equal to V1 over 11/5. No. I1 See, this is me again wanting to get confused. I lost my pen. So this is me again being confused. Wrong. Oh, wait a minute. Yeah, I mean, this is give me my pen. This is okay, right? That's current is voltage divided by resistance. But now we want to find Y1, which is going to be, so Y11 is the current I1, V1 now, V1 over 11/5 divided by V1, right? This is all at V2 equals 0. So this is equal to, the V1s will cancel, 5 divided by 11, which is, I'm just guessing, if this is 0.09, this is about 0.45 mhos, I tend to think of it. I notice the text uses this thing called capital S, almost like it's the S parameters. Easy to get confused there. But nevertheless, it's going to be the same thing. 0.45 or 450 milli-S's. It comes out something like that. So very similar activity, right? I mean, we can find all of them in this way. I've just gone through one part of it. But you can see how easy it is. I am anyway, so used to dealing with impedances. Admittances, you just have to remember, oh, am I inverted or not inverted? But in truth, admittance is the inverse. You just got to be very careful when you try to convert circuits like this, and go from there. All right, the next one will be a short one on the hybrid parameters.